Okay. We have 7:32 on the clock, so I'm going to call this meeting to order for the May 12th monthly meeting. Okay, so first item on the agenda is the April 14th meeting minutes. Are available on the members area on the website. And the only error that I think or omission on there is that we didn't have the name of the person who seconded the last month's meeting for that particular item on the agenda. So if anybody remembers who it was, please come and see me. We'll get that changed. So has anybody had a chance to look at it and see if there's any errors or omissions? No. Okay. We'll call a vote. Can someone make a motion to accept the meetings as posted? Okay. Motion by Mary Paulson. Do I have a seconder? You have to yell out your names or we don't miss them. Pardon me? Okay, Dave at the back. Okay, thanks. Any questions? None. Okay, we'll call for the vote. All in favor? Opposed? Being none, motion carried. Okay, moving on. I forgot my joke.
Clayton, can you hear me?
Oh, yes.
So who is Dave at the back? What's his last name?
What's your last name, David?
Lindsay.
Can you spell that? Did you get that? Tom?
Lindsay, okay. Yep.
Okay. Okay, good.
And one more thing, Clayton, on the agenda. So I'll be hosting Astro Imaging Corner tonight, not Dave Mussel.
Oh, that's like because you weren't going to be watching a hockey game. That'll probably come right when the Oilers are on a power play. I'm hoping. Okay. Okay. Actually, I got instead of an astronomy joke to start things off with, I have more of a joke that's pertinent to what's happening these days. So what do the Winnipeg Jets and the Titanic have in common? They're both pretty good until they hit the ice. Okay, that was bad. I could have used the Vegas, but I didn't want to give them anything to put up on their whiteboard. Okay, the treasurer's report.
Okay, I don't think we need visual aids for this. So it was a rather quiet month, the month of April for the center. In our general account, we had a starting balance of $71,322. There were no expenses out of that account all month, but we did have some credits. We had almost $300 go in for membership dues. We had our GST rebate for the first half of the year, or sorry, the last half of last year come in. So it was almost $400, and we received a donation in the amount of $150 in the memory of Bruce. In the casino account, we did have some expenses out of that this month. We had a starting balance of $121,400. We ended the month at $117,702. A major purchase, kind of the first major purchase for our PlaneWave project came through. So the Schwanke camera was bought in the last month for $3,500. And then we had some shipping charges for outreach materials. The Bob Drew Fund remains at $2,516. That's unchanged since March. So things are starting to heat up. Northern Prairie is starting to happen. So I know many of you have probably started registering. So that's there's been a lot of those come through the account in the last little while. Just a quick reminder, because maybe you haven't done this in the last little while. If you do have expenses, there's an expense report that you can fill out. That's on the it's on the Edmonton Center website. Just go to forms and there'll be an expense report there, and just fill it in and send them in to me, and I'll get you your check or your internet transfer as quickly as I can anyway. Any questions?
We'll get a motion to get that. Do we need that? No, I don't think so. No. Okay. Thanks, Jeff. Okay. Next we have is our guest speaker for tonight, Dr. Martin Connors, and his speech is going to be on seeing through things, the invisible solar system. Now, Martin had been a member of the RASC since 1960, which led to an education in astronomy and physics and becoming a professor at Alberta University. He is still associated with his alma mater, Western University in London, Ontario, as an adjunct professor collaborating on planetary science topics. Most recently, he was a visiting researcher at UCLA in Los Angeles, investigating space physics using the NASA Themis mission. In 2024, his book, Invisible Solar System, was published, and he is now working on a second book. So, Martin, I'd like you to come up, and when Frank gets you going, you can take off.
Okay. Thank you very much. I should point out I was an RASC member since the late 1960s. I'm not trying to pull a Franklin Lodi here. But I was just looking through books when I was making this, and I discovered an award from the RASC, which was dated January 2nd, 1975, 50 plus years ago. So that's a long time. Anyway, I've been interested in space, and obviously I lived through the Apollo program. And so there will be some quizzes in this talk. So who can tell me who the astronaut is? Wow, that is good. How do you know? Okay, where is John Young? In this photo, where is John Young? And there is a wrong answer here.
In the reflection of the screen, the face shield.
He's actually about half a meter above the moon because he's actually jumping. Okay, so let's see. So yes, this is Apollo 16 astronaut John Young, and he's jumping. You can see his shadow just underneath where the notations are. April 21st, 1972, long time ago. And in the background, in the shadow of the lunar module, you can see a thing that looks like a sea star. So one of the questions that lunar faker people, conspiracy theory types say is there are no stars in the background. So Stanley Kubrick did this on a soundstage and he forgot the stars. Well, actually, Stanley Kubrick was a kind of a detail guy. I have a bit of difficulty with these lights, and the stars of the planetarium confuse it a bit. But if you do look at that carefully, you could actually see that Stanley Kubrick did put stars. And the reason you don't see them in the actual photographs of the real astronauts is that they use very short exposures because it was pretty bright. And so the stars don't come through. Although I'd love to get hold of the original negatives and see if you can't see them, because I think you probably could. But anyway, Stanley Kubrick did a very good job. It's actually just slightly after dark. And if you remember, Stanley Kubrick set this in Tycho, and the moon has the Earth rather low on the horizon. Tycho is very close to the South Pole. So I think this is all pretty accurate. But the point of the talk is that there's a lot in the solar system that we can see, surfaces of things like the moon, and that gets a lot of press. So this talk is about what you can't see in the solar system. And so we can start out by examining what that sea star was. And so the fellow on the right there is Dr. George Carruthers, who designed and sent to the moon this ultraviolet camera. And it's a 75 millimeter diameter F1 Schmidt camera. It recorded on some sort of film, which was then digitized, and apparently you can get all the images somewhere. But it actually shows that from the moon on the right, they photographed the stars. And more importantly, and more relevant to this talk, is that also the Earth was photographed. And if you look at the Earth there, you can see the bright side. That's not particularly surprising. There's ultraviolet coming from the sun and being reflected. There's also the so-called ultraviolet day glow, which is that the atmosphere itself gives off light from the ultraviolet. And if you look more carefully, you can see at the bottom right, actual ultraviolet aurora. And actually at the top, it extends a little bit beyond where the terminator would be. That's the northern hemisphere aurora. And then more surprisingly, the equator is outlined with ultraviolet light as well. So there is some activity happening at the equator of the Earth that gives you ultraviolet light. And of course, in keeping with the idea of invisible, we can't see ultraviolet light. So what happens if you look at that more carefully and a longer exposure? And that was part of the idea of this camera. So on the left, you can see the things that I just mentioned, the aurora sticking out on the bottom left, the equatorial band, and the day glow. And I think the little bump that you can see on the right is just a star near the Earth. But the point is, there is fuzz around the Earth. Is that just it being out of focus or something? No. That is actually the outermost atmosphere of the Earth. And here's an even longer exposure on the right. And you can actually see that that is really fuzzy and extends all around the Earth. So this is Earth's outermost hydrogen atmosphere called the geocorona, or the really distant exosphere of the Earth. And so the SOHO, you've probably seen many images from SOHO because it images mostly the sun. And when you have a coronal mass ejection, by the way, I don't talk about auroras in this talk, but when you have a coronal mass ejection launched towards you, SOHO can show it. But here it has been turned around to look back at Earth. And when you do that, you see outlined in contour lines the geocorona of the Earth. And believe it or not, the geocorona has only been imaged very few times. And so this is one of them. SOHO normally faces inward toward the sun. And you can actually see the orbit of the moon has been plotted as a gray ellipse, and the position of the moon on the date that this was taken. Now that's actually projected outward, but even so, the moon has around 0.2 atoms per cubic centimeter of the Earth's atmosphere. So probably Apollo astronauts would have been surprised to find out that even though they were standing on the moon, they were still in Earth's atmosphere. So this is the geocorona, and the solar wind itself is denser than that. So you might say, well, why doesn't the solar wind just blow away the Earth's external atmosphere? You can see that it looks pretty spherical. It's very undisturbed. Well, the point is at those low densities, stuff just goes through. So these solar wind ions and electrons just go past the Earth's atmosphere and don't affect it whatsoever. No interaction with the solar wind. And so what's going on to allow us to see it is that if you look at hydrogen atoms, then on the upper left, that is the ground level. That's the way a cold hydrogen atom likes to be. It's a proton surrounded by an electron cloud. And if you fire in light, like ultraviolet light, a fair amount comes from the sun. You can see on the right is the spectrum showing the visible. And when you get out in the far ultraviolet, it's really tapered off. You'd be beyond the left end of that graph, but there's still enough to get interactions going of light. So the solar wind doesn't interact, but light from the sun does. And so what can happen is from the bottom, which is the top right energy level, you can get electrons kicked up to one level above, and then they'll just fall down again, and then they give off the light again. So the light is coming straight out from the sun, it may interact with an atom, and now that atom will give that light off in any direction. So you don't have to be on the line from the sun to see it. In fact, if you're on the line from the sun, you see an absorption line. So anyway, that's how this happens, that there's a geocorona, and the bottom left is what the atom looks like when it's been excited, but it goes down. Now, the other thing that often happens is that there's too much energy and it just shoots the electron off. Then it's game over. You're not going to get any more light from that atom because it's so thin in space that it won't interact with anything. So, however, it turns out that it isn't necessary that it's just going to go to that same level and then come down again to give you what's called Lyman alpha light in the ultraviolet. It could also get kicked somewhere up higher. And if it gets kicked up somewhere up higher, that would be in this middle row. And then it'll come down, and it may come down to the second level. And if it comes down to the second level, we're talking about a lot less energy. It's not ultraviolet anymore. It's light that we can actually see. And in fact, one of those lines is probably pretty familiar to many people in this room because it's H alpha. And by the way, I work with H beta with auroras a lot. So if I ever say H beta in this talk, I really meant to say H alpha. So anyway, that's red light. And here's an interesting connection, because if you look at the right, this is the cluster M37, Gemini, I think. Anyway, people know where to find it. And it turns out that M37 has a planetary nebula inside it. So that one of very few clusters that have such a thing. And if you observe that with a spectroscope, then you'll get this. This is the spectrum. And you see that H alpha is labeled there. It's red light. The units here are more archaic units. Well, astronomers still use them, called angstroms. So you just divide by 10, and you've got the wavelength in nanometers that we normally use these days as physicists anyway. And you notice it's labeled geocoronal H alpha. So here they're trying to take a picture of a planetary nebula that's giving off from hydrogen that's in it, and plus some planetary lines that you might recognize from your filters, planetary nebula lines that you might recognize from your filters. But there's this big geocoronal line. So my question for advanced observers is, could you actually observe the geocorona? There's a challenge for you. Now, just some notes on H alpha. For one thing, Brian Martin pointed me to this very beautiful image that he took showing Orion. And there's this amazing loop, Barnard's loop in Orion, that although it's not proven definitively what it is, it's got to be a supernova remnant. And my favorite thing is in the upper left corner there. The reason it's my favorite thing is because it's a combination of a cluster and a nebula, and that's the Rosette Nebula, which is shown on the right. Sorry, I sort of lost where I got that from, but beautiful nebula. And what's happening there, you have this cleared out central area, but with bright blue stars. And so the bright blue stars are doing exactly the same thing that I showed you happens with the geocorona. You've got ultraviolet light coming from those really hot stars and boosting up the energy levels in all the hydrogen that's around it. And then it falls down again. And part of the falling down process gives you this beautiful red H alpha light. So it's just like the geocorona. And so Brian has that nicely imaged Barnard's loop on the left and the Rosette Nebula in the upper left. And of course, at the lower left is Sirius, and then Orion majestically there. Now, if we look at Brian's area a little bit better, we can put it in astrometry.net, and it'll fill in the constellation outlines for us. And I was kind of looking at this and thinking, you know, what's a nebula? And monoceros, that means unicorn. So that's where the Rosette Nebula is, probably the coolest thing in monoceros. And then if you look on the Worldwide Telescope even further, you get lots of, I mean, there's lots of hydrogen in the universe, right? So you get lots of H alpha emission. And so the lineup isn't exact with the previous image, but you see Barnard's loop outlined there. And then the Rosette Nebula is the sort of middle of that rather intriguing stream of stuff on the left. And I'm not even sure what's up at the top. So yes. So anyway, this is just exactly the same thing that's happening with Earth's geocorona. So connection of the solar system to the distant parts of the galaxy. Now, Carruthers, who I showed you a picture of before, has a new space probe that is going to be launched soon called the Geocoronal Observatory. So what he did in sending a telescope to the moon, they will now send this to the Lagrange 1 point between the Earth and the Sun, and it will look back towards the Earth to continuously image the geocorona. Because as I mentioned, it has very rarely been imaged. There were these experiments on the moon, and then they turned SOHO around once. So it has not been studied very much. They don't know what the dynamics is. They don't know what causes it to change. So again, I think it's possible that amateurs could do some H alpha imaging at the same time as Carruthers is doing this. And an interesting project that's going on right now at the University of Toronto is the Dragonfly. And so each of those is a Canon lens. I think you can see Canon, product placement there. But they all have a CCD behind them instead of a standard Canon camera. And there literally will be thousands of these. And so the aim is to build actually the biggest telescope in the world, or so the University of Toronto people tell me, by having many, 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 many of these on mounts. And they are imaging in H alpha, but bear in mind that the universe is expanding. And so H alpha gets redshifted. So they're mostly operating at redshifts. The geocorona has no velocity really. So it's at zero redshift. So they're not actually going to look at the geocorona very much. I'm trying to convince them that maybe, again, one man's or one observer's signal is another's noise, and maybe they should look at the geocorona, but I don't know if it'll happen. So it happens that the Caruthers will be launched together by SpaceX with the IMAP, which is the Interstellar Mapping and Acceleration Probe. And it is the successor to a spacecraft that produced most of its data about 10 years and plus ago, called IBEX, the Interstellar Boundary Explorer. And so this is very topical because it just completed vacuum testing the other day and is now at Kennedy awaiting launch. Although the latest I heard is maybe the launch won't actually happen this year. But first, let's get back to what is IMAP going to do besides just being launched along with Caruthers. So let's talk about the solar wind and, in fact, the heliosphere. So what is the heliosphere? Well, it has, first, not to talk about what it is, but what its boundaries are. It's bounded by shock waves. And so where can you see a shock wave? A really cool place to see a shock wave is in your kitchen sink. So if you shoot water down from a tap, this is just my sink and a baking pan, you shoot water down from a tap, and I'm sure everybody has seen this, it expands very quickly. And that actually is, for water, supersonic. And the reason that it's supersonic is because if you started a little ripple near the outer edge, it can't go upstream. The water is moving fast enough that the ripples are carried to the edge, and that's where you get all this bubbling and stuff happening. But that water is just going out, and that's what the definition of supersonic is that waves can't go upstream. So you can create a supersonic simulation in your sink. And of course, we always think of supersonic as being with jets. So on the left is a shadowgram of a jet showing the shock waves at the beginning and the end of the supersonic zone. Now, Eugene Parker, who passed away a couple of years ago, but not before he was able to see the very rare thing of a satellite named after a living person. Caruthers unfortunately passed away several years ago, so his spacecraft is named after a dead person. But Eugene Parker was able to go to the launch of his own spacecraft, which is the now famous Parker Solar Probe. But Parker became famous actually in 1957 with a paper where he realized that the solar corona, shown at the upper right and showing its line emissions that show its very high temperature in the millions of degrees, how does it get that way? I won't be discussing in this talk, but if it is that way, then Parker realized that it's not possible for the atmosphere just to gently float into space. It had to be supersonic. And so he wrote a paper about this, and one of the reviewers, I've had some bad reviews, but never quite utter nonsense, come back, and apparently that did happen. But Subramanian Chandrasekhar, himself very famous astronomer, and by then the editor of the Astrophysical Journal, had been treated very badly by somebody that we'll see again later in the talk, and that was Arthur Stanley Eddington. And so he maybe had pity on Parker, and he thought, well, let's publish this and just see what the reaction was. Well, that became one of the most famous papers in space physics because Parker was right. And so Parker Solar Probe is now investigating the inner parts of the heliosphere, which is down near the sun, where it all starts to get supersonic. And so, excuse a few graphs, but I hope they're interesting graphs. And also they're kind of relevant because Parker Solar Probe is down there right now. So the vertical red line or orangish line PSP minimum are, that's how close in Parker Solar Probe gets. And when you're very near the sun, it's maybe the opposite of what you might expect. The solar wind is actually kind of slow in near the sun, and it gets supersonic further up. And so the subsonic region is at the lower left, and it depends what the actual temperature of the corona is. But you'll notice they're all times 10 to the 6th Kelvin. That's 1,000,000 degrees. So the million is about as cool as it ever gets. And then there will be times when it's hotter. And of course, in the real world, it's not going to be uniform everywhere. But for the theory, you say that. So this is in solar radii, and you see a vertical yellow line. It's a bit hard to see, but that's the surface of the sun. And so obviously the line should not continue through that, but that's just the way I drew them. And so the dashed line is where it goes supersonic. So when you get up to 10 solar radii, most of the time it's going to be supersonic unless the temperature is kind of cold. But Parker Solar Probe has seen subsonic solar wind. So it's achieved its goal. By the way, it's very hard to get into the sun. Not only does Parker Probe have extreme heat shields, but it has to do sophisticated orbits bouncing off Venus all the time to lose energy, to fall down towards the sun. So basically, if we look on the lower right, this is a larger scale. So astronomical units is the radius of the Earth out from the sun. And you can see at 1, if you look at the black line for 1 times 10 to the 6, 1,000,000 degrees, that's sort of typical. You'll get typical speeds, which is the solar wind is going at 400 kilometers a second past the Earth, which is supersonic. So we're inside a supersonic flow. And of course, that relates to auroras, which I'm not going to talk about. But let us indeed talk instead about shocks. So the Themis probes, which are from UCLA, and I was just down there working on them, kind of cool stuff, even though they were launched in 2007. The novelty still hasn't worn off. This is a Themis probe going out from the Earth. And I just want to point out that what the Themis probe is seeing was first predicted by Queen Elizabeth's physician, William Gilbert. And in 1600, he produced a book called De Magnete, and he said that the Earth is a huge magnet, which of course we now know is true. And he even did sophisticated things like pointing out that a compass needle would like to dip. And there is a different kind of needle called a dip needle that shows that. This can be used, for example, for navigation. It was very important at that time for that purpose, as well as pointing north. You could kind of determine your latitude by the dip. And so we start out with William Gilbert's prediction. And at the lower left, we're in the Earth field. And you'll notice the very lower left graph, that's rather large. And then you get smaller and wiggly, quite a bit disturbed. And then at the lower right, you're in the solar wind, and there's a much smaller magnetic field than there is near the Earth. So the Earth is magnetic. Solar wind's a bit magnetic, but not really terribly magnetic. But then if you go to the very upper graph, you can see that that's the density, and the density near the Earth is low. So where the magnetic field is high, the density on the left top graph is low. Then you get this compressed region, which is also well seen in the middle where it's that orange smudge. That sort of shows you the compression. And then you're out in the solar wind, which is mostly blue in that middle. So it's cool, but there's just one flow at one speed is that red bar across. And then you can see the density has gone down again. So the solar wind is a bit magnetic, it's not very dense, and it's flowing very fast, is the story about the solar wind. And again, all of these circumstances, when it interacts correctly with the Earth's field, gives you auroras. And again, no auroras in this talk. So if you do look, however, at the magnetic field in the solar wind, that was first seen, I think it was probably on the previous slide. I'm almost scared to go back. Can I go back, Frank? So it actually was, I've lost track of where it is. Let me just tell you verbally. It was actually the Soviets who first observed the solar wind because they sent a probe to the moon. It was called Luna, maybe this is on the next slide, so I'll just get a bit ahead of myself and skip that if when we get there. Luna, it missed the moon. So bad luck, the early days of the space age. These days they don't miss the moon that often, but it ends up in interplanetary space, and it did have devices to detect plasma and magnetic fields. And hey, there's all this plasma here going very fast. So the Soviets actually discovered the solar wind. Parker had predicted it 3 years beforehand. So he was confirmed. Naturally, of course, the Americans did a better job because they got a spacecraft that was actually supposed to miss the moon and go to Venus. And they got the recordings similar to the ones that are on the left. These are actually a little bit later. So the solar wind is full of waves. That part I'm not going to talk about. But the other weird thing when you're out there in the solar wind, this is now for about a half a year of data at the upper right. And you'll notice that the solar wind points in either of two directions. This is angle, up, down. And, it flips all over the place, but it basically goes to being 45 degrees, minus 45 degrees, or 135 degrees, which is also 45 degrees. So they're either pointing in towards the sun or out away from the sun, and you don't get any other values really, apart from all this wiggling around. So that is called sector structure, and it was actually rather puzzling when it was discovered. So it is actually reflecting something called the Parker spiral. And so the wind comes out, and this kind of exotic looking diagram shows the wind's direction outward as arrows. So blue arrows. And I also try to show the density by having many of them when you're near the wind. And as it goes away from the sun, it spreads out and gets less dense. But the weird part is you'll notice the arrows are short near the sun, and then they get faster as it goes out. And so this is the acceleration of the solar wind to supersonic speeds. But the other weird part is because the sun is rotating only about once a month, rather slowly, but because the sun is rotating, the magnetic field gets twisted into what is now called the Parker spiral. And so the Parker spiral at Earth is 45 degrees. And depending on whether you're above or below, what you can see on the left as kind of a current sheet, you'll get pointing in or pointing out. And that explains that. It's sometimes referred to, and unfortunately I didn't put a slide in about this, but it's called the ballerina skirt, because this thing is flipping. If a ballerina was rotating, her skirt would go up and down, and that's what's happening with this magnetic field that's mostly in the plane. We've only ever had one spacecraft called Ulysses go out of the plane of the Earth's orbit. It's a lot of energy to get out of the plane. And the way they did that was they shot it to Jupiter, and then instead of studying Jupiter or something silly like that, they just used Jupiter's gravity to flip it way up. And then it was able to go above the poles of the sun and study what the solar wind was like there. We find that it's quite different from the solar wind in the plane of the Earth's orbit, which is also the sun's equator, and it's fast solar wind. Now, if you look at your eclipse photos, you're going to see near the pole, it looks kind of like a dipole. And that's indeed what happens. And solar wind can just go out along those lines, whereas magnetic field lines, whereas near the equator, you've got all these twisted lines, and twisted magnetic fields hold the stuff in. So the slow solar wind is what manages to escape from all those twisted lines near the equator. So another clue about that was a fellow called Ludwig Biermann, and this was in the early 1950s. So I just thought this was very great German workmanship, that he made 3D models in brass of the solar system, and he had a little comet. You can see the comet looks sort of like in the middle there, almost like a fly sitting on his device, and he could orient this, and he studied the tails of comets, and he found that we all know there are two tails to comets, a dust tail and an ion tail. He found that the ion tail always pointed away from the sun. And so this indicated that something was sweeping out from the sun and pushing the ion tails back. And indeed, we know that that's what's happening. Now, Isaac Newton in 1680 was very impressed by the comet of 1680 and correctly drew a diagram showing on the left it's coming in and it hardly has any tail. It was observed then, but not very bright. And then when it was going out, it had this huge long tail. Interestingly enough, his tails are all pointing to the sun. So he didn't really realize that. So Isaac Newton didn't discover everything. And finally, just for Edmonton and advertising for Athabasca, in 2061, because Halley's Comet is about a little bit past halfway to coming back again, Athabasca will be the very best place in the world to see Halley's Comet, because with its tail passed back, pointing always away from the sun, that you can see in this sequence is a yellow dot below the horizon. It will pass across the northern horizon and then go from having its tail this way to being vertical over several nights to being horizontal almost the other way. So book your tickets now. The Athabasca Lodge is taking reservations for the Halley Comet viewing in 2061. Now, Halley's Comet, of course, has not been recovered yet. When it's on its very elongated orbit, very far from the sun, there is no tail, there's nothing to see. And so I have no real idea. I think I know the guy who's going to do it, but I don't know when. Sometime they will manage to pick up Halley's Comet coming in again, and then you'll be able to book the exact dates in Athabasca, because right now we don't have them nailed down. There are weird things that happen to comets when they're in the outer solar system, so we don't have it precise. So most of the time, comets are part of the invisible solar system too. They're just a little ball of rock and ice, and you can't see them except when they have a tail, when they're in the inner solar system. So anyway, I was talking about shocks, bracketing, the heliosphere. And so this is a possible schematic view of the heliosphere. Now, we don't really know what's outside the heliosphere very well. So there is speculation that there's a flow through the galaxy and that our heliosphere looks sort of like a comet. And other people say that it looks more like just a sphere. There isn't much flow pushing it back. So we don't really know that very precisely yet. But this is obviously a diagram by somebody who has kind of the comet view. And I'm not sure, Frank, could you dim the lights a little bit? So the middle shows a similar effect with the star Betelgeuse, of course, from Orion and from that picture. I think everybody can see. Yeah, there it is. It's better with the lights down a bit. So you can see this bow shock. So Betelgeuse itself has an immense stellar wind. It's a red giant pushing out material. Eventually, it's probably too massive to just have an ordinary planetary nebula, but it's shooting off its atmosphere and eventually will explode or something will happen. But as that atmosphere goes out, like a solar wind, only much more intense, and hits the interstellar medium, it forms a bow shock. Our own sun has a bow shock, probably not as observable from far away as Betelgeuse's is, but that might be another very challenging project. In fact, I've already got somebody who's an active imager on the hook for that. Can you image something really faint like that, really close to a really bright star like Betelgeuse? So there's a challenge for you. It is only about 1/4 degree away, by the way. So really tough object. But the Voyager spacecraft have in fact gone through the shock, the termination shock at the edge of the solar system. So again, think back to the sink and the water coming down and shooting out, and then there's a shock at the outer edge. Well, there's also a shock where the solar wind cannot remain supersonic. It has to slow down to merge into the galaxy. There is material out there, very thin material, but to merge into it, you can't be going supersonic anymore, and there is a shock. So the shock is shown at the right, which is data from Voyager 2. And so it's from very shortly after it went through the shock. So you can't really see it too well, but believe me, the changes do occur that lead to the red line. And so basically there's an abrupt transition at the heliopause, and LISM means local interstellar medium. So we actually do have spacecraft in interstellar space right now, Voyager 2 being one example. And then Voyager 1, I'm sorry, not a perfect memory. I think Voyager 1 also has entered. And then New Horizons that went past Pluto is one of the fastest spacecraft ever. It will enter as well. So soon we'll have 3 spacecraft in the galaxy, no longer in the solar system. So I got on this talking about the heliosphere by talking about the IMAP spacecraft, and that's led by Dave McComas at Princeton. And so what if you want to get information from the very outer solar system, but you've only got so far 1 or 2 spacecraft, they're only sampling 1 or 2 points. It's pretty big out there. So can you image that? And the answer is no. It's gas that doesn't really give off detectable radiation, so you can't just image it very easily. So one very cunning way to do it is that normally you cannot see particles because it's all magnetized, and charged particles spiral around field lines. Now, if you're intrigued by cosmic rays, which are intensely energetic, we don't know really where they come from. And the reason for that is because the entire galaxy has a magnetic field, and these cosmic rays are charged particles, so they get in a magnetic field and they spiral around, and soon you don't know where they came from. The radius of those spirals may be, in some cases, as much as a light year, but they're still spiraling, so you soon lose track of origins. But luckily, there is a process called charge exchange, and it produces what are called energetic neutral atoms. And so what's red in my diagram has charge, what's blue doesn't. And so what happens is that a charged particle is spiraling around in the left, and it hits a neutral particle, and then charge exchanges so that it doesn't have a charge anymore, but the neutral particle gets its energy and flies off in a straight line. And so that particle is then called an energetic neutral atom. The advantage of being neutral is it just ignores magnetic fields, just goes straight through them. And so you can actually make images using neutral atoms. Now, there aren't very many of them, but IBEX was successful. And, you know, you send these things up to see what the situation is, and you don't know what you're going to get. So here's what we got. It was called the IBEX ribbon. And it's in the bottom middle there. It looks like a nice ribbon, very intense. And that was at solar minimum. And then under solar maximum conditions, several years later, it had changed. And so what's causing it? What's making it change? We don't know. And so IBEX told us that it was there. It's called the IBEX ribbon. And now IMAP will go up and possibly, with better instruments, give us some clues about what's really happening at the very outer boundary of the heliosphere. So let's completely change. We're going to go from the outer boundary to the inner depths, basically of our sun, but of any star. And so I have a trick question for you. And anybody can yell out an answer. And I don't hear any cheering yet. I don't hear any booing yet. But anyway, let's have some audience participation. Why is the sun hot in its center? Any ideas? Gravity, fusion. Gravity is a better answer than fusion, believe it or not. So here is a hint. Anybody know who these guys are? Timon and Pumbaa. And what did they say? It's all gas. No worries also, of course, but it's all gas. So the answer is that normal stars are hot because they're big balls of gas. You don't need fusion. So if you have a big ball of gas and it's not collapsing, it's just sitting there, it's hot in the middle because you need hot gas to produce pressure to prevent it from collapsing. And so all big balls of gas are hot. And it is not because of fusion. They have fusion because they're hot. But what does fusion do? trick question number 2, what do nuclear reactions do if they don't heat the star up? What do they allow? So Kelvin, Lord Kelvin, from Glasgow, made a fortune actually with electromechanical apparatus. Everybody knows him as the guy for temperature. He is shown with some apparatus here, and actually the undersea cables didn't work at first. As you can imagine, in the day of yore, when they wanted to have communications across the whole British Empire, if you went to huge expense to lay down cables and then they didn't work, that was terrible. So he solved the problem using the newly invented by another Scotsman, Maxwell's equations. How do you actually make submarine cables that work? And he got to be immensely wealthy. And I think a lesson is to be learned there in our own political times when we see universities under attack, that the British Empire and modern technology got going because of a need, and Kelvin solved that need and actually was pretty wealthy, but also studied stars, because when you have any money, as everybody here who spends money on telescopes knows, you should spend it on astronomy. So anyway, Kelvin did study this problem and knew what the temperature of stars was. Just one little problem. If a star is hot and it's hot on the surface, it gives off light, and that's a loss of energy. And so it's going to change with time. So I've given a long-winded answer here, or hint. So what do nuclear reactions do if they do not heat stars? My graph is there, and unfortunately I took a version of the graph that I didn't label properly, but the sun is at the right most, so it goes along pretty flat and then goes up. So that's at the 12 billion year mark. And then it's 1.2 solar masses, 1.4, and the one that doesn't last very long, only 1 billion years, that's a 2 solar mass star. So what nuclear reactions buy you is they buy you time. So the nuclear reactions allow stars to stick around and not change. And as you can see from the flat lines, that's called the main sequence. They don't change very much during that time. Then they run out of fuel, and now you're a red giant and trouble happens. But nuclear reactions allow stars to live a long time. In the case of our sun, 12 billion years, we're only about halfway there. So trick question number 3, can fusion reactions occur in stars? Everybody of you modern people knows the answer. Some were even trying to give the answer, which isn't really quite the right answer to that question. But can fusion reactions occur in stars? We're going to go back 100 years and look at the basic physics of that. And so I've got to get this DVD. I just found out about it, Einstein and Eddington. So Eddington, who's the guy, remember I mentioned about Chandrasekhar, who gave Parker a chance? Because Eddington gave him a hard time. So, but Eddington was nevertheless a great astronomer, and he was involved with Einstein in the sense that he was very involved with relativity and the proofs which will come at the very end of the talk, about the Einstein theory of gravitation. But he wrote this book, The Internal Constitution of the Stars, and he said, it is held that the formation of helium from hydrogen would not be possible at stellar temperatures and must be ruled out. We do not argue with the critic who argues that the stars are not hot enough. We go tell him to find a hotter place, which is an English gentleman's way of telling his opponents to go to somewhere. Anyway, so that was the problem, was that in 1926, when this book was written, it was not thought to be possible to get hydrogen or any other atoms, because they didn't even know necessarily the stars were entirely made of hydrogen or almost, and helium, to cool. You can't get stuff close enough. It's got to move fast and get close to have a reaction. So you can't have nuclear reactions in stars as of 1926. So fortunately, 1925 was a big year in astronomy. One of the things not very related to this talk, but I will mention that while I was in Los Angeles, I had the privilege of seeing this original plate. It was actually on display in an art museum. But anyway, this is the famous VAR plate with which photographing the Andromeda Nebula, Hubble found that it must be very far away. So distant galaxies existed prior to 1925. That was not very well established. So the whole scale of our universe wasn't even known 100 years ago. But another subtle thing that wasn't known 100 years ago was that stars were made of hydrogen and helium. And so it was the efforts of Celia Payne, later known as Celia Payne-Gaposchkin, who lived 1900 to 1979. So she did detailed studies of the spectra of stars, showing their atmosphere and how their atmosphere absorbs light coming from below. And she found that stars had to be made mainly of hydrogen and helium, which was an amazing discovery. And it was so amazing that she actually wrote in her thesis, the outstanding discrepancies between the astrophysical and terrestrial abundances are displayed for hydrogen and helium. In other words, she had just found that hydrogen and helium are very common in stars. Apart from your kid's helium balloon, we don't have much hydrogen. It's bound up in water, but it's normally too light. That's why it goes off into the exosphere, the geocorona that was the first thing I talked about. So there's hardly any hydrogen here on the surface of the Earth and hardly any helium, but she found that's what stars are made of. But she wrote in her very own thesis, the enormous abundance derived for these elements in the stellar atmosphere is almost certainly not real. I mean, if I'd written that in my thesis, it wouldn't be Dr. Martin Connors speaking to you today. Anyway, so interesting. But why would physicists back 100 years ago think that even if there was hydrogen and helium there, which they admitted there must be some, why would it not have nuclear reactions? They were known at the time that Eddington wrote this. Well, the nuclear pioneer Ernest Rutherford had done an experiment showing that atoms had nuclei prior to the early years of the 1900s. That effect wasn't even known. So what he had done was shot radioactive particles, alpha particles, towards gold, and he found that astonishingly, some of them came right back at him. And so previously they thought, well, atoms are just charge and a blob, and if you shoot something like that through, it'll just go through. Well, most of them did, because atoms are mostly empty space. But some of them, the 170s, for example, bounced right back at them. That's not the point of this slide. The point of this slide is that they can't get any closer because they get repelled. And so physicists back 100 years ago thought that it was never possible to get atomic particles close enough to each other to have them react because stars were too cool. 100 million degrees sounds like a lot, but it's not enough to get stuff going fast enough to have the atoms actually hit. So how would you possibly have reactions if stuff can't even hit? And so in 1927, that's a year after Eddington was writing, Heisenberg developed his uncertainty principle that basically told us that everything is fuzzy and wave-like. That's not the entire part of the answer, because George Gamow, a year later, took this concept further, and he realized that there was such a thing as tunneling. So if things are really waves, then the top diagram would say, well, sorry, if things are particles, the top diagram would say that you can get in a certain distance and you can't go any further. You can't go up that hill and over it. You have to stop and turn around. So that's a particle. And also if you're inside, you're trapped inside forever. You can't get over that hill. What Gamow showed instead was if you had waves, yes, the waves have trouble getting through that, but they can actually get through. And so the problem that astronomers thought 100 years ago that stars were not hot enough to have nuclear reactions could be gotten through because protons could tunnel using their wave-like nature to get into the vicinity of others. Now, the amount of overlap would be tiny, but it's enough to have reactions. But there's another problem that they didn't know about. And that is that we now know that when they thought protons were elementary particles, by the way, the neutron had not been discovered at that time. It was only discovered in 1930. It turns out that protons and neutrons are very similar to each other. One has charge, the other doesn't. but in other aspects, they're very similar. And so if you have a free neutron, it actually changes into a proton. Now, protons do not do the opposite very readily. But what can happen is that if they are near to another proton, one of them can turn into a neutron. And that is what's necessary to get the basic reaction that happens in the sun going. Now, they show you these beautiful diagrams. This is really a nice one from Cosmos at your doorstep. But I've added the little caveat there because they don't really tell you that the first step takes 10 billion years for your average proton. So your protons are just floating around doing nothing for 10 billion years. That's your fuel. It doesn't do anything. So that is the slow step in the reaction. And then once they manage to form this special 2 hydrogen, that's the next step over from the 10 billion year little slashes, then everything happens really, really fast. And that's when you get your reactions. So basically, protons do not want to change into neutrons, and that's the real reason that the sun is stable, but does have fusion reactions, but they're slow. So what was the difference between what's happening in the sun and the Big Bang? So the Big Bang had particles, the red are protons, the blue are neutrons, and they basically formed out of nothing. I'm not going to talk about the Big Bang, not an expert on the Big Bang anyway, but once you do get them, now you've got protons and neutrons, and they are able to react very readily. And so often it's referred to as the first 3 minutes. That's when all the excitement happened in the Big Bang, was through time. The times are labeled there. I've sort of developed this graphical method of putting what you've got on top of a graph that shows what you've got. And so basically you start having deuterons, that's the ones in the second group over, just 2, and then 3 is tritium. And then eventually you've got helium, and at T equals 300, 5 minutes later actually, but it doesn't start immediately either. Now you've got protons left over. They didn't have any neutrons to react with, and helium. So all the neutrons are gone. Neutrons decay anyway. If there had been any left, they just decay. But they're nice and stable if they're in helium. So you end up with lots of hydrogen, some helium, and that's basically what we have in stars. So at this point, then you get hundreds of millions of years of boredom before stars form, although they're debating that now with James Webb, et cetera. But anyway, this is the Big Bang, very different from fusion in the sun right now. So they formed together and reacted. The key thing here is that protons and neutrons get together with what's called the strong force, and protons themselves to change into neutrons, that's called the weak force. Again, you're talking your 10 billion years, not seconds. And so that's the difference between the strong force and the weak force. So let's just talk about what goes on in the details here, because it comes back to the invisible solar system. So we have this solar furnace, and in the 1940s, it was realized that this must be what's going on. The problems the initial scientists had about it's too cool and all that were resolved. And you had a famous Burbage, Fowler and Hoyle paper that basically gave our modern view of how stars are powered. But the lower mass stars like the sun are dominated by this type of reaction of 2 protons. Bear in mind, again, there should be a 10 billion year marker at the left-hand side. But when they do get together, they give off an electron antineutrino and a positron. Well, the positron is in the middle of the star, the sun, surrounded by lots of normal matter. And a positron is an anti-electron. So it will find an electron and bam, they're gone. They give you gamma rays. And, you know, in Star Trek, when they say turn on the positrons, or the dilithium will give positrons or whatever, antimatter reactions to get going through space, the sun generates 10% of its power through antimatter reactions. That's those positrons finding electrons and poof. But The other thing that comes out is these electron antineutrinos, and by comes out, I mean really comes out. Neutrinos do not interact with basically anything, and so they just go through the whole sun and just come streaming past us. Now, we're always told in astronomy books about how many of them are passing through our body every second. It's actually a small number compared with how many photons you're going to get if you go sunbathing, but it's still pretty impressive that these are just going through. And by the way, the fact that it's night and the Earth is there between us and the sun doesn't matter. They just come through the Earth. So anyway, just on the lower right are recent observations by a device called Boraxino. And that is showing on the left the proton-proton neutrinos, which it turns out have a continuous spectrum. So the energy along the bottom and how many of them are, which is the vertical axis, it's just a spectrum, a continuous. And then there are lines also depending on the reactions. And so we also know from these that other types of reactions take place in the sun a little bit, but most of the power in the sun is coming from protons interacting with protons. So I'm going to now go on to the last topic, completely changing topics, still just sticking with the theme of invisible. And I'm hoping that we did get going a little late, so I'm excused a tiny bit, but this really is heading in on the last topic. And so that topic is the discovery of Neptune. And so we can use gravity as a probe in the solar system, and now increasingly in other star systems like exoplanets, for example. If you see an exoplanet behaving weirdly, chances are there's another exoplanet there. And we do use that. It's called transit timing variations to discover. So the pioneers, though, in using gravity to explore the unseen parts of the solar system were Adams and Leverrier, who were in the competing countries. This was in the early 1800s. So they were in the competing countries of England and France. So there was a lot of national prestige involved in this. But basically, the vertical line in this graph is the year of discovery of Uranus, which was 1781. And that was by our favorite Herschel, who built his own telescopes. He was a musician. All the professional astronomers hated him because he was an amateur, but he was better than they were. So anyway, but one of the things he also did was very systematic surveys of the sky. The new general catalog, for example, is based on Herschel's initial surveys where he cataloged thousands of objects. And I don't know if Warren Finley is here tonight, but he's an expert on Herschel and has observed the Herschel catalog, et cetera. But anyway, basically he was scanning the skies. He thought he discovered a comet. Then he got a little bit more information. He realized the orbit was circular. And yeah, if you looked at it a bit more closely, it didn't look as fuzzy as a comet. And so he had the great idea, hey, this is great. I'm going to call it after King George, because that might be a nice thing to do to get some money. Anyway, that didn't stick. So eventually it was called Uranus, the god of the skies. And the trouble was that it wasn't really that faint. And so people had been observing the skies with telescopes since Galileo. So if you actually looked back, you could find maybe this object sometimes, and they did. So all the points on this to the left of the line are pre-discovery observations where somebody said, oh yeah, I'm making a map of the stars. There's one, there's another, there's another. Only that one was actually the planet Uranus. And so they traced back, but when you traced it back and you took what you knew now, you found that Uranus was in the wrong position when it had been observed before. So what could be causing that? So the answer was, well, it's probably another planet. And so Adams and Leverrier tried to use the techniques of celestial mechanics to figure out about the other planet and do some detective work. And if you could do things right, you could tell astronomers where to look for it. And so basically, these are the orbits that they had. I drew them up from the data that they supplied. And you can see that the real orbit of Neptune is the blue line, and both Leverrier and Adams got it wrong. So they had very bad orbits for Neptune. But it turns out that around the year of discovery, which was 1846, all these sort of errors canceled out and they actually gave you the right position. So then it became a question of Adams could write to British astronomers and say, hey, you guys should go observing. And they didn't really do it. Whereas Leverrier wrote to German astronomers and they did. And so as a result, just having new charts that they had just made the previous year, they looked and they found, oh, there's this little star and, we're pretty good. We're Germans. We're rather meticulous. If there had been anything there last year, we would have made a dot and there's no dot. So that really is the planet. And so it's hard to see, but it says on the left, Neptune beobachtet, which means Neptune observed. And then underneath it, it has a ditto mark and then calculated. So they've got two dots there. One was the observed and the other was the calculated position. So they discovered Neptune based on predictions from gravity, which gravity, of course, is part of the invisible solar system. And so Leverrier, and I like the title of this book, Magnificent and Detestable, because apparently he was not a nice guy. But he was persistent. So he figured, okay, I won the battle because it was Leverrier's observations. I won the battle with Adams. And by the way, Adams was a very nice gentleman and he took it all very graciously. But Leverrier, I'm the greatest astronomer in the world. Maybe I can make another prediction. And Brian gave me this beautiful photograph of a recent transit of Neptune. So you can see a spotless disk except for one spot, which is Mercury. I don't remember when that transit was, but it was maybe 10 years ago or more. And you can observe where that spot is extremely accurately. And they found that it was 43 seconds of arc in the wrong place every century. And Mercury, I think, is only at most 10 seconds across on the solar disk. So, you're talking whole planet diameters difference and, really well known. If you added up all the attractions of all the other planets and did a good job on it, you still couldn't account for 43 seconds of arc, per century. Small, but definitely detectable. So anyway, it turns out that Mercury is advancing in its perihelion. That just means that the orbit is sweeping. I've made a plot where this effect is vastly exaggerated, although some black hole systems do have that degree of it. But anyway, the perihelion advance led to not a new planet. Leverrier wanted to discover a planet called Vulcan. I don't know where Mr. Spock got that idea, but Leverrier had it first. And there was no Vulcan. It was, in fact, due to Einstein's general relativity that this effect was happening. And so that is the end. So using gravity and an aspect of the invisible solar system, you could make predictions and find a new physical effect, which was the general theory of relativity. Now, we live in a visually spectacular solar system, but some of the things that are invisible, I think, are also very spectacular. Thank you.
Do we have any questions for Martin?
Uh-oh. My old professor.
Martin Connors, as you've just seen and heard, has a remarkable ability, more so than anybody else I know, to take somewhat disparate facts of the universe and bind them together through the history, the development of ideas. It was a wonderful presentation.
Thank you very much. I'm sure there are things that could be criticized in it.
Any other questions?
It's rather fascinating that you said that some particles, I think it was the proton and neutron, one, if they get close together, they gain a charge. Is it a transfer charge or is it a new charge that is created?
Well, a neutron can turn into a proton. If you have a neutron, everybody thinks protons, neutrons, you can have a neutron. Well, you can't. A neutron will hang around for 10 to 15 minutes and it'll change into a proton. And so the way that it does that is through this weak interaction. So let's see, to get the math right, it's a proton, it's a neutron, so it has no charge. So if in the end it's going to be positive, it has to kick out an electron. So you get an electron out of that, and then you'll get a neutrino. So what I was showing before was an antineutrino. So you get an electron and a neutrino, and then your neutron is now a proton.
So it's a transfer of the electron.
Yes.
Oh, okay.
And then when the opposite happens, after you 10 billion years, when the opposite happens and a proton gets near another proton and is able to change into a neutron, then you get a positron, and that takes away its positive charge, and an antineutrino.
And it only takes 10 million years.
Billion.
Billion years.
Billion with a B. Yeah. If it didn't take 10 billion years, then stars would collapse, hot gas, and then they would immediately explode if it took any shorter than that.
Okay, we've got time for one more question. Anybody local, or we got to get somebody on the Zoom call? Oh, sounds like that's it. Mark.
Okay, I didn't hear any cheering or any booing.
I don't want to hear anything.
Oh, he
I'm
doesn't want to know
recording
the
game.
score. Okay, thank you very much.
Thank you, sir. Okay, now, again, thank Martin. I'll let you figure this out. Okay, so next, Murray Hunt is going to give us an update on the observers group. Murray.
Totally different change of pace now. I'm more of a stargazer, so more I'll be talking about things you can see. And just up a few slides, this was one of our many get-togethers around Edmonton. There's usually 10 or so people coming out each time, often different people. And this is Deer Mound Park. We found it pretty close, well, it's in Sherwood Park. And it's a pretty good site for being within the Edmonton Light Dome. And as you can see, people are all set up there. This was early in May. And let me see. A little later, we got together. We went to Blackfoot staging area. So mostly been trying to just do low-key observations around Edmonton. We went out to Blackfoot. And as you can see from Corvus, nicely centered right in the middle of the frame. These are all pictures Alistair Ling took. Much darker skies. And double stars, for instance, we're trying to star hop a bit using binoculars in the city. You just see the star out there. It was so much nicer. In Deer Mound, though, 2nd of May, we're starting to transition a bit, or I'm encouraging some from going out and looking and seeing to actually making some observations. So a couple of us that one evening, 2nd of May, were looking at Mars, and we knew it was going right close to the Beehive cluster. So this is one field of view, 2.7 seconds about of arc, and just a sketch I made of the cluster with Mars heading by. What I was hoping to do was do a series of these so we could see Mars against the steady backdrop of the stars as it moved along. But with clouds, I only saw it one other time from my backyard through binoculars, through some trees. So I just did that one. But once we can start making observations, we can see what is moving out there in my refractor. Then I just took a picture of it and did a horizontal flip, basically. So this is north up, west to the right, and it's more of what you would see in binoculars. And more. So one more. Now, Alistair sent this to me as well. And this is my last slide for tonight. Alistair sent this to me, and I thought at first it was kind of a test because I didn't know what it was about. Number four on to your left, that is the asteroid Vesta. And on 2nd of May, it was in opposition, Earth and Vesta in opposition. So we were closest to it. And actually Earth was overtaking it. So if we looked at it, actually, this has gone up for tonight. Alpha is Spica, constellation Virgo. So just from Spica, 2-star hops over, Mu Virgo, and there is Vesta. It's the brightest of the asteroids. And in fact, May 2nd, it was about 5.7 magnitude, easily seen in binoculars. So we could look up on May 2nd and see this dim star and think nothing more about it. Somewhat like perhaps Neptune through the years. And if we make a sketch, plot that star, come back, and you can follow the red line along. It's actually in retrograde motion because Earth is overtaking it. And by June 21st, Vesta will come around and right down along the line between Mu and Kappa Virginis. And it will do a big arc and come right around and then resume its eastward travel. And my plot, I'm going to take this on, and I'm hoping I can see it enough times to plot this. And could challenge anybody else who would like to look for Vesta. As I say, it's about the 3rd largest asteroid between Mars and Jupiter, but it is the brightest. And it will go from about 5.7 magnitude to around 7 magnitude by August. And so just something that we'll be watching for. And just the other thing, our next regular observers meeting will be next Wednesday, not Wednesday, but the Wednesday after, May 21st, 7 o'clock to 8. And everybody's invited to come on Zoom. A lot of us are new stargazers. Several are medium and advanced. So everybody's welcome. And thanks very much.
Thanks, Murray.
Okay. Thanks, Tim.
Okay, so what we'll do to keep things moving a little quickly here, we'll go into our break right now. But during the break, hopefully we'll have the trivia question up. And if we can keep the break down to 5 minutes, that would be great.
Let's all go to the lobby. Let's all go to the lobby. Let's all.
Okay, I think we'll get started here again. Which spacecraft was Laika, the first living creature sent into space? What makes a planet a dwarf planet? And what is the name of the first space tourist? That one's a toughie. So we don't have too many announcements so far. We got an MPSP update. I don't know if it's Marion or Susan. Marion, okay. Oh, Susan. Whoa. I got it right.
You did. Thanks. Hi, thanks, Clayton. I'm Susan, part of the Northern Prairie Star Party planning team. And I was thinking of a happy motto that we would have, and that is, if we plan it, they will come. Anyway, registration opened for Northern Prairie on Monday, the 5th, a week ago. And we only have 3 sites left. So we have the online registration on the Northern Prairie website, RASC Edmonton. So if you are still interested in attending, we have 1 10 site, 2 unpowered site, and a small powered site at G9. So you're welcome to register. We're really happy that we have 2 speakers for our Saturday afternoon. We're working on our 3rd. And we'll have our schedule and t-shirt design probably within the next month. So looking forward to registrations for day visitors. And if you are interested in a powered site, you could still go to the southern part of the campground to get your site. And then we will have some ways of people being able to have their telescopes in the north part if you are not camping in the north part this year. On top of that, we have a Friday workshop with Alan Dyer, as well as green laser pointer certification that Clayton will be doing. And this will be an annual part of our Northern Prairie Star Party. And we're required to do it every 3 years, is it? Every 3 years. We're having a swap and shop again this year with some really interesting bits of equipment and things that I've already heard about that will be coming out for that. Barbecue, of course, and observing at the Black Nugget Lake Observatory too. And we're going to have those famous donuts as well on the Saturday. So registration, if you're coming out for the day programs, it doesn't close till the end of August. So you have some time to think about it. And but we are looking forward to having you come. If you have any questions, you can talk to me after the meeting. Thanks.
Thanks, Lizzie. Okay. This is not on the list, but Frank just indicated that after the meeting, if anybody wants to stay around and watch the last part of the third period, it'll be up on the dome. Okay, so Jeff sent this over to me, and this is a bursary that the RASC makes to the university on a yearly basis, and is known as Doug Hube Award, I believe is what they call it. Anyway, it's a bursary, and this year's winner, man, that's small print, received $1,300 anyway, but I can't read the name. It's just too small. But anyway, so congratulations to that person. If anybody can read that. Okay. Anyway, we want to say thanks to the RASC for funding that, and why did my mount up there is okay. Next, we'll have Mark come up with Book of the Month. You went back to the library.
Briefly, good evening. Greetings from the Kimball Library, from Rosemary Ball and I, co-librarians. Library is open before and after the meetings for books to lend out to members. During the intermission, I brought out a few of the most recent books of the month and put them on the ledge. I'll probably be doing that in months in the future. This book of the month for this month, Bringing Columbia Home, was recommended by our very own Lori Walton, and she has kindly provided a review for the book, which I will read right now. So it's Bringing Columbia Home, a 2018 book by Michael Leinbach and Jonathan Ward. On February 1st, 2003, the Space Shuttle Columbia, carrying 7 astronauts, disintegrated over Texas upon re-entry, about 15 minutes before it was due to land at Kennedy Space Center. As families, friends, and aerospace workers waited anxiously in Florida, wondering why the shuttle had not landed, people in Texas were jolted by loud booms and smoke trails in the early morning sky. Each one of the 10,000s of pieces of debris produced its own sonic boom. Wreckage from the shuttle rained down for 30 minutes along a 400-kilometer path across East Texas and Louisiana. Large metal tanks and potentially radioactive or poisonous objects were landing in schoolyards, on roads, and throughout the very dense bush characteristic of the area. The ground search operation to recover shuttle pieces and fallen crew members became the largest in U.S. history. NASA initially focused its recovery efforts on locating the remains of all 7 fallen astronauts, then shifted to a massive ground search to recover every fragment of the shuttle. Identifying the cause of failure was crucial so NASA could fulfill its obligations in building the International Space Station. Thousands of volunteers, many from the small towns in East Texas, or retired NASA employees, helped in searches coordinated by NASA, law enforcement agencies, the FBI, FEMA, and the Forest Services. Citizens of small Texas towns offered tremendous support for the search teams. Particularly effective were the wildfire crews contracted by the U.S. Forest Service, including Native American firefighters representing nearly every Native American tribe and nation in the western U.S. In the final stages of the search, 2 people lost their lives due to a helicopter crash. In total, over 80,000 pieces of debris were recovered, about 40% of Columbia. It was determined that a small piece of foam from the external fuel tank struck the left wing of Columbia during liftoff. During re-entry, superheated gases penetrated the wing and led to the shuttle's disintegration. The remaining space shuttles were grounded for more than 2 years and then used to complete the building of the ISS and to repair the Hubble Space Telescope before the fleet was retired. This book, co-authored by the launch director for Columbia's flight, is one that I read over and over again. The search and support by the local residents, volunteers, and government agencies is one of commitment, compassion, and coordination, showcasing the very best of humanity. I highly recommend it. And that's Lori Walton's review. Thank you very much, Lori. And the book is available immediately after the meeting, so just hunt me down. Thank you.
Thanks, Mike. Actually, if anybody has the Smithsonian Channel, they did a very good documentary on that just recently. I think it was a 3-parter, 3 1-hour episodes that covered the actual, the whole history of that particular accident. Okay, next up we have Astro Imaging Corner, not with Dave Muscle, but with Tom Owen. Tom.
Okay, so I'd like to welcome everybody to Astro Imaging Corner number 146. First, I'd like to say a big thank you to Dave Muscle for so capably pinch hitting for me last month. So first, some commonly used terms for people who are new to Astro Imaging and might be tuning in. Subs are referred to, and they are individual short exposures. Noise is the static you hear on your car radio when you're trying to tune into a Blue Jays game in Calgary. Then these are the names of the filters. LRGB are the broadband filters. HAO2 and S3 are narrowband filters. Messier is the catalog of what is now 110 deep sky objects, first compiled and published in 1774 by Charles Messier. And IC, which you'll often see in front of numbers of objects, it's the abbreviation, it's the index catalog. And it was published in 2 parts by Danish astronomer Dreyer, first in 1895 and the second in 1908. And it not only supplemented the new general catalog with new objects, but also corrected many NGC entries, which is why some deep sky objects will have both catalog numbers. So our first image is from Alan Hobbs. It's the Witch Head Nebula. And he says that it's also IC 2118. It's an extremely faint reflection nebula, believed to be an ancient supernova remnant or gas cloud illuminated by nearby supergiant star Rigel in the constellation of Orion. The nebula lies in the Eridanus constellation, about 900 light years from Earth. And this was taken at the Casitas de Gila guest house in New Mexico near Silver City on March 24th. The astrophoto has 30 subs of 2 minutes each, with a 60-minute integration time. The photo was taken with his Celestron RASC 8 and the ZWO AS 2600 MC camera with an Optolong L enhanced filter on a Skywatcher EQ6 Pro mount. And it was processed with PixInsight and Photoshop. So excellent photo, Alan. The next is the Seagull Nebula by Alan. He says this is IC 2177. It's a large region of nebulosity located approximately 3,650 light years away in the constellation Monoceros, the unicorn. The nebula includes an H2 region, open star clusters, dark dust clouds, and reflection nebulae. The Seagull Nebula has an apparent size about 7 times that of the full moon. It was named the Seagull because its complex of dust and gas forms a shape reminiscent of a seagull in flight. Okay. I think it looks more like a Romulan man of war, but I could be wrong. The nebula is composed of interstellar dust clouds and hydrogen, helium, and other gases that are ionized by the energetic young stars formed within the nebula. The radiation of the new stars causes the surrounding hydrogen gas to glow with a reddish color in long exposure images. This was also taken in New Mexico near Silver City on March 21st. 15 subs of 3 minutes apiece for a 45-minute integration time, again taken with the RASC 8 and the 2600 MC camera with the Oplong L Enhance filter. And it was processed with PixInsight and Photoshop. Another excellent picture, Alan. So this is a photo I took. It's known as Markarian's chain. It's a string of galaxies in the constellation Virgo. The fuzzy blobs that you see there are elliptical galaxies. And as you can see, they don't have a defined structure and consist mainly of old stars. The galaxies that look like thin streaks are actually spiral galaxies seen edge on. And in the middle of the string are a pair of gravitationally interacting galaxies nicknamed the eyes. They're distorting each other's shapes. There are actually a lot of galaxies in this picture. I counted well over 20 in total. The bigger appearing galaxies range from 50 million to 65 million light years away. So I imaged this April 24th at Pigeon Lake under Bortle 4 skies using a Takahashi TSA-120 telescope, a TOI 130R focal reducer, and the 2600 MC camera. 2 hours and 40 minutes total exposure using mostly 2-minute subs, stacked with APP and processed using star tools. This is, I'm still testing out the MC Pro, 2600 MC Pro. I got it very recently. So I put it on M5 and Serpens and quickly realized when the first sub came in, I was better off setting the gain to 0. So this is the result of 61-minute and 32-minute exposures for a total of 2 hours, again using the TAC TSA-120 at prime focus. The image has been cropped about 25%. Subs were stacked with APP and again processed using star tools. No flats or darks were used. Most estimates put the number of stars in this globular cluster at over 100,000. Again, I'm trying for the natural look these days, and yes, but those stars really are colored blue and gold. So this is from Ray Wiens, the Sombrero Galaxy. It was taken with the Williams Optics 132 millimeter with a QHI Y268C. That's an APS-C size sensor camera. I may be wrong, but I think that's the equivalent of the 2600 MC. The telescope was mounted on an iOptron CEM60 mount. This is approximately 40 minutes of exposure with 300-second and 600 seconds individual subs. He says it was quite close to the horizon as I was shooting through the trees at Blackfoot Dark Sky site. The image is cropped quite a bit. And here we have from Ray M97 at the top and M108 at the bottom. And this again was taken with the same rig that he used to take the Sombrero. The telescope, it was stacked in APP and processed in Lightroom. These are 18 exposures at 300 seconds each for a total exposure of 90 minutes. He said he was very happy to get both in the same field of view. Very nice juxtaposition there, Ray. Then we go on to Hans S. John. Sorry about not capitalizing your middle initial. This is NGC 2403. He says that he's got 2 images for us tonight. He says both were taken with an edge, a 9.25-inch edge HD and a 0.7 focal reducer so at 1650 millimeter focal length or f7, the 2600 MC camera, off-axis guided, and from Bortle 7 and 8 skies in Sherwood Park. So he says this is a fine-looking spiral galaxy, somewhat reminiscent of the famous M33 in Camelopardalis. He says Messier perhaps overlooked it, Then Herschel gave it this designation. Exposure time was 18.5 hours in RGB and 5.5 hours in HA03. And you can really tell the HA, the little pink knots are nebulae in the spiral arms. Very great, really a great image. And here he has the Owl Nebula, M97. He says it's usually depicted with few features, except for the quote eyes, end quote. So I tried to bring out the low contrast details a bit more. Exposure time was 70 minutes in RGB and 320 minutes in HA03. And I've never seen the Owl Nebula look like that. That is a tremendous photo, Hans. Well done. Finally, we have Warren Finley's sketch of the Whirlpool Nebula, M51. He says, I did this sketch viewed on April 27th, 2025 through a 22-inch f3.3 scope with a 26 millimeter OVNIM eyepiece. The actual sketch is 6 inches by 5 inches and was done using soft pastels applied with brushes, plus white and black charcoal pencils. I did some very minor touch-ups in Photoshop. I had inadvertently smeared the white pencil for a few of the stars. So I really love this image. And as Dave said last month, we love sketchers here at Astro Imaging Corner. Berta Beltran, if you're on, I'm looking at you. And I need hardly remind everyone that sketching at the eyepiece is a tradition that was started by Galileo himself. So you sketchers are in good company. So let's see your fine work. So in conclusion, please send your images to astroimagingcorner@edmontonrasc.com. I'd like to see not only sketches, but I want to see your images if you're just starting out doing images. I mean, this is for the members, and you can be justly proud. If you take an image, you should be justly proud of what you have done because not very many people do it. So with all that, that's my presentation. Thanks very much.
Thank you, Tom. Okay, so we'll move on quickly here to the trivia answered. Okay. So what spacecraft was like a first living creature sent into space? It was Sputnik 2. What makes a planet a dwarf planet? Size and shape. And what is the name of the first space tourist? The answer is Dennis Tito, and it cost him $20 million to go up to the. Now I don't know if that was on Mir or on ISS. Can't remember. Over here, out of the way, and we'll get to the final announcements here, which aren't many. You heard from Murray on what's going on for the observers group, so I won't rehash that. We'll do a quick cartoon of the month here. I had to put this one up. It's from my wife. She said if I don't, I'm in big trouble. So this is hers. Your resume said you had experience related to astronomy. Could you elaborate? And he says, I spent a lot of my time staring into space. My grandson when he's at school. Back here, so our next meeting is, should put that back up there. It is Monday, June the 9th, and we'll have two presentations that night. One will be from Mark Zelsick talking about the non-collucent cloud, and we'll have another short presentation from Gina Paysan talking about the film that she has produced and filmed, part of it being done in this particular dome, and it had about 8 or 9 RASC members in the film as well. She'll talk about the film, what it was about. The name of it was Physics for Poets. That was the story of Galileo just prior to him going to his Inquisition. And there will be a small trailer as well. And those will be the two presentations plus our regular meeting agenda. So I think everybody wants to get back to the hockey game, so we will call this meeting adjourned.
Thanks, everyone.